So what I really like about this area, that's the theme for today's talk, so Univalent Foundations, Homotopy type theory, or whatever you want to call it, is it's absolutely stuffed with highly intelligent people at the opposite end of the age spectrum from me, young people. And Floris van Doorn, who's the next speaker, is an example of that. He's a graduate student at the University of GitHub. I mean, sorry, CMU. And he's going to tell us about developing HOT in some also rather young theorem-proving system called Lean, which you may have heard of, and which you haven't. You're going to hear more about it tomorrow, I guess, from its lead developer. Okay, so Floris, thank you.
Thank you for the introduction, and thank you for inviting me to speak. So I will talk about developing a Homotopy type theory library in Lean. So my talk naturally consists of two parts, Homotopy type theory and Lean. So I'll start with Homotopy type theory. As we've already seen in the talk today, in Homotopy type theory, types are interpreted as spaces. And so one natural research area is then, can we investigate properties of these types just like how Homotopy theorists investigate spaces? So can we, for example, compute algebraic invariants like homotopy groups and other properties of types? This is a method for homotopy theory, which is more general than just doing homotopy theory in the traditional sense, because if you do it in homotopy type theory, it will be true in any model of homotopy type theory. So I don't think there's a talk specifically about models of homotopy type theory today, but there are many such models. You can do it constructively. And it's easier to formally verify in a proof system, and particularly this third point I want to explain in my talk and give some indication in my talk that it is actually true. We will use the univalence axiom and higher inductive types, which I will also explain what these higher inductive types are, which are already mentioned a couple times. So compared to Martin Ascardo's talk, I'm really in the second part of homotopy type theory, doing homotopy theory. So as we've seen in the previous two talks, a type is really interpreted as a space. So in a type, we can have points A and B, and then there may or may not be paths between those points. So there might be a path P and a path Q. And then there can be higher paths between those paths. So we can have a path from P to Q, which is like a two-path in the type. And so these are elements of the identity type. So I will denote the identity type just by this single equality sign, because that's really how I think of the identity type. Like, it's an equality of two terms, except that it also has higher structure. Paths are elements of the identity type or the equality type, and then we have higher paths between those types, and this goes on and on. So this identity type, or this path type, or equality, this is a very central notion in homotopy type theory. So it corresponds to equality in logic under the Curry-Howard isomorphism, and to path spaces in homotopy theory. And so this gives three different ways to think about the identity type. So you can think, say, like the identity type is this family of types, which is generated by a reflexivity term. Logically, it's the least reflexive relation, or maybe a bit more precisely, the free reflexive relation. And in homotopy theory, this corresponds to the fact that if you take a path space where you keep one point fixed, then that space is contractible, because you can, if you have any path with one point fixed, you can sort of contract the other point in the path down to that single point. So that's a contractible space. Note that these three formulations do not mean that every proof of equality is reflexivity. That there are proofs of equality which are provably not equal to reflexivity. This notion is made precise by something called path induction. So this is the precise formal statement of path induction, and here is the more intuitive explanation. So the formal statement says if I have any family which ranges, which takes a path, so a family of types indexed over a path, and I want to prove or construct an element of this family over an arbitrary path from A to X. To do that, it's sufficient to prove or construct an element of just over the reflexivity term. That is the precise statement of saying that the equality is generated by reflexivity. Note that I say proof/construct here, and that is because in type theory these two notions sort of are conflated. Like proving a theorem is basically the same thing as constructing an object. So intuitively this means that if I have a path P from A to X anywhere in my proof, and as long as its right-hand side is X, is a variable, then I may assume that P is just reflexivity and that this variable X is just A. So path induction is very useful and is very useful in proving many things. So here's an example which I want to prove using path induction. So this is the concatenation of paths. So if I have a path from X to Y and a path from Y to Z, I want to construct a path from X to Z. And of course this also corresponds to transitivity of equality. And so the informal proof so a proof goes like this. Well, so Q has as right endpoint Z, and that's a variable. So I may assume that Q is reflexivity and that the Z is the same as Y. And now I just need to construct a path P concatenated with reflexivity, and that now has type X equals Y, because Z became the same as Y. And we can define that because we have an element of X equals Y, that is namely that is P. So we can define this to be equal to P. Maybe this seems a bit sketchy to you, but I can show that this is a valid proof, namely this is the proof in Lean. If I have a path P from X to Y and Q from Y to Z, then I get a path from X to Z, and the proof is just I do induction on Q and then it's exactly P. This is the whole proof in Lean. And we can also prove other properties now about, for example, concatenation of paths. Steve mentioned this, that there's a sort of groupoid structure of paths. If we have 3 paths P, Q, and R, then the concatenation is associative. And that also has a very simple proof, namely we do induction on R, and then after we have done induction on R, then R became reflexivity, so then the goal is this thing. And now, well, we defined concatenating with on the right-hand side reflexivity, we defined that just as the thing on the left-hand side. So this reduces just to P concatenated Q, and this also reduces to P concatenated Q because this reduces to Q. So I can prove that just by reflexivity. So this gives, just for path algebra, very nice short proofs. So another thing which I will use in my talk is truncated types. They've been already mentioned in 3 different talks, so I will just give a picture of them. So this is a picture of the whole universe of all types. And then some types in them are truncated, and some types are not truncated. So at the bottom of the hierarchy of truncations, we have the contractible types, the -2 types, which have exactly 1 point. Then 1 level higher, we have the propositions, which are the types which have at most 1 point. Then 1 level higher, we have the sets. Those satisfy the uniqueness of identity proofs, or axiom K. That means that for any two points in the type, there's at most 1 proof of equality. And then we have the 1 types, which says that all paths are sets. And then in general, the n+1 types say that all the paths in that type are n types. And so this hierarchy is cumulative. So if I have a 0 type, then there's automatically a 1 type and a 2 type, and so on. And then at the top, there are also types like the 2-sphere, which are not truncated in any level. One thing, so if we have a type which is not yet truncated, we can truncate it. So that is the end truncation, which has also been mentioned with the special cases of the propositional truncation. So if you have a type A, we can form the end truncation of A. And so the end truncation is sort of the best approximation of A in the universe of end truncated types. So what I mean by that is that I have a map from A into the end truncation, and then it has a universal property, namely for any map from A to X, where X is assumed to be end truncated, then there exists a unique map from the end truncation of A to X, such that this triangle commutes. So this is sort of, you take a type and you sort of push it down to the end truncated level. And you do that by sort of forgetting all the higher structure in the type. So one thing we can do now in Homotopy type theory is, for example, define the fundamental group. So if you have a type A with a point A0 in it, so that's a pointed type, then we define the loop space of A. And the loop space of A is just paths from the base point of A to itself. And that is again a pointed type, namely it has the S-point reflexivity in it. And in this loop space, we have operations which correspond to the group operations. Namely, we have multiplication, which is given by concatenation. We have inverses, which are given by path inverses, and the identity is given by reflexivity. And these satisfy the group laws. However, as Martin also mentioned, like we want that groups are sets, and this is not in general a set, so this can have higher structure. What we do is we take the set truncation of this loop space, and that is called the fundamental group. And that sort of kills off all the higher structure so that we get a set, and that this is actually a group. And we can also define the higher homotopy groups in a similar way. We just take the loop space n many times and then take the set truncation. So these are algebraic invariants sort of a space, and the idea is that if a space is very complicated, these might be easier to construct or to find. So this is a bit different than the traditional definition of the fundamental group. So traditionally, you would define the fundamental group as like continuous functions from the interval into A, such that f0 and f1 are both sent to the base point, and then you mod out by homotopic paths. Two functions in the two paths in the fundamental group are considered the same if they are homotopic. So this definition requires all kinds of definitions in math. So it requires a whole library of stuff before you can actually formulate this. We need real numbers, we need the interval, we need continuous functions, we need homotopies of paths, and all that is needed just to define the fundamental group. Well, in HOT, it's almost primitive. Like I almost gave you the whole definition on the previous slide. Constructions in homotopy theory are much closer to the basics in homotopy type theory, and that makes it very useful to formalize in a proof assistant. For example, so in HOT you can formalize the fundamental group in less than 100 lines. And I want to contrast this with a paper by Boazan, who is in the audience here, and he has a paper which is to appear at ITP. And his conclusion contains the following paragraph, which is, starting from the axioms of set theory, we formalize the definition of the fundamental group, as well as many other results in set theory, group theory, and point set topology, and real analysis. The entire development contains 30,000 lines of theory and 3,500 lines of ML code, taking the author about 5 months to complete. So this is a very impressive result. So he uses a new automation tool he developed to make this possible. But so it requires a quite big development to start from the axioms from set theory and to do homotopy theory. Well, in homotopy type theory, you can do it much more easily. Also, once you have defined the homotopy group, it's easier to work with it in homotopy type theory. For example, if you define an operation, so classically, if you want to define an operation on the homotopy group, you have to prove that it's invariant, that it respects homotopies, so that it does the same on two homotopic paths. But in HOT, all functions you define are automatically satisfy this property because homotopic paths are just equal paths, and every function respects equality, of course. So another new idea is in homotopy type theory is higher inductive types. So the analogy I want to use here is that higher inductive types combine ideas from inductive types in type theory and cell complexes in homotopy theory. So inductive types in type theory are types which are generated by some constructor. So for example, the natural numbers is generated by a zero element and a successor. Then for example, the direct sum can be considered also as an inductive type. It's not actually recursive, but all its elements are generated either by points in A or by points in B. And actually the identity type is also generated just by reflexivity in some specific way. And in homotopy theory, we can build cell complexes in sort of a similar way. We can build a space by taking points, then we take paths between them, we take two cells between those paths, and we build up a space that way. And in homotopy type theory, you can combine these two ideas sort of in higher inductive types. So for example, here's the circle. So the circle is generated by one point constructor, the base, that's a point in the circle. And then we add one path in the circle, namely we add a loop which goes from base to base. And like every inductive type, all higher inductive types have a recursion principle and an induction principle. So for example, the recursion principle for the circle, which Steve also mentioned, is that if you want to define a function out of the circle, we need to define what it does on base. So we need to define f of base. And we need to show that f respects the loop. So we need to give a path in A from f base to f base. So that is similar to the induction principle, or for example, the natural numbers or the sum, which specifies how to define functions out of the type. And using univalence, we can prove, for example, that the fundamental group of the circle is the integers, which the idea is that, well, if the loop space from base to itself, well, we can go counterclockwise any amount of times, or clockwise any natural number times. So that gives the integers. That is sort of the idea. And we can actually prove this in HOT using the univalence axiom. So another example of a higher inductive type is the suspension. So the suspension is generated by 2 points, a north pole and a south pole. Oh yeah, the notation for the suspension is a bit unfortunate. It's traditionally written as a sigma, and that is sort of overloads the sigma in type theory. But I'll use a sigma just on this slide for the suspension. So the suspension is generated by a north pole and a south pole, and then we add, for every point in A, we add a path from the north pole to the south pole. And so for example, if we just have 2 points in A, then we have a north pole, south pole, and 2 paths from north to south. And if you sort of draw that picture, then you see that you get something which looks like a circle. And actually, you can prove inside HOT that the circle is the same as the suspension of the 2-element type. And this way we can define higher spheres, which is very nice because they are studied a lot in homotopy theory, by saying, well, the 0 sphere is just the 2-element type, And then the n+1 sphere is defined as the suspension of the n sphere. Okay, so now I want to move from just talking about Homotopy type theory to talking about lean. So there are various proof assistants which support Homotopy type theory. Already they were mentioned in previous talks. So there are 2 libraries in Coq. There are one main and a couple other libraries in Agda. There's a library in Lean, and then there are experimental proof assistants which implement cubical type theory. So there's cubical TT, which stands for cubical type theory, and there's a new one developed at CMU, which is still under development, which is called RedPearl. And so I will of course talk about Lean and for Homotopy type theory. So Lean is an interactive theorem prover developed principally by Leo, which is in the audience. It was sort of announced in summer 2015, so it's a very young proof system. It's open source, that's standard nowadays, but it's nice. So Lean has a standard and a hot instantiation of the kernel. So one remark is that the new version of Lean, which Leo will tell all about tomorrow, doesn't support Homotopy type theory, at least yet. So we developed the Homotopy type theory library in the previous but stable version of Lean 2. So these are some features of Lean. So it implements a powerful dependent type theory. It's written in C++ and has support for multicore. It has a very small trusted kernel, especially for dependent type theory. The kernel is very small. It has a powerful elaborator. You can construct proofs using terms or tactic. So in a way similar to Agda, or in a way or tactics like Coq. There's a nice Emacs mode which checks proofs on the fly, and in the new version of Lean there's also a VS Code mode. And there's a browser version of Lean which runs in JavaScript. So the kernel of Lean is really small. It implements really just these 4 things. So there's a hierarchy of universes, type 0 in type 1 and type 2, indexed over like an external natural numbers. And these are not cumulative. So if you have a type in one universe, it doesn't automatically live in a higher type. But you can of course lift it. There's a construction which lifts it to a higher type. It supports universe polymorphism, so you can define a function at sort of all universes simultaneously. So this is the identity function in an arbitrary universe. It has dependent products, and it has inductive types natively. So and these are a la de Pierre, which where only you add the constructors and the recursion principle for the inductive types, and things like pattern matching are not in the kernel. So for dependent type theory, the kernel is very small, as I already said. So there are multiple reference checkers which can check the proofs, and they are about 1,500 or 2,000 lines of code, and all kinds of things. So Coq and Agda have some of these things, features which Lean doesn't have in the kernel, and they are very prone to bugs and inconsistencies. So regularly an inconsistency is found in Coq and Agda, and that is often because of one of those features. So Lean doesn't have a termination checker, fixed point operation, pattern matching, and all these things. However, on top of the kernel there's a powerful elaborator which figures out all the information you leave implicit in your proofs. So it can figure out implicit universe levels. You don't have to write universe levels explicitly. Those will almost always be figured out by Lean. It has a powerful unification process. It can do computational reductions and some features which are quite standard in proof assistance. So like overloading coercions, type class inference, You can do definitions by pattern matching and tactics. So for example, you can still do proofs by, or definitions by pattern matching in Lean. They will just internally be represented as just applications of recursors. So there's a nice dependent pattern matching package which compiles all these definitions down to just recursors of type theory. Yeah, so dependent pattern matching is notoriously quite difficult to compile, but Lean does that all automatically for you. So the Homotopy type theory library in Lean is a large library for homotopy theory, and we really focus on doing synthetic homotopy theory, so doing homotopy theory and homotopy type theory. On top of Lean, in the homotopy type theory library, we add two things. We add the univalence axiom, which we postulate just as an axiom, and we add two higher inductive types, namely something which we call quotients, which are not the usual set quotients, but it's this higher inductive type, namely you start with a type and sort of a binary dependent family over that type, and then it has two constructors, namely for every point in A you get a point in the quotient, and then sort of for every element in the relation R you get a path from the endpoints of R. So sort of the paths in the quotient are freely generated by this relation R. And this, and so a second higher inductive type we add are n-truncations. So n-truncations can also be restated as higher inductive types. And we add these as kernel extensions so that they also satisfy some computation rules which we want. The homotopy type theory library contains sort of the following things. So it contains a very good library with the basics of homotopy type theory. So things like path algebra, properties of equivalences, properties of truncation levels, truncated types, truncations, consequences of the univalence axiom, for example, that function univalence implies function extensionality, various higher inductive types, and a library of pointed types. It has a library for category theory, and then the main focus is synthetic homotopy theory. And then there's a separate repository where we put active formalization projects with the intention that if they are sort of stable, we will move them to the main hot library. And that there are many contributors to the hot library, some of them which are in the audience, and there's more than just listed here, but these are the main contributors. In Lean we just have two higher inductive types, but actually just having those two higher inductive types, we can construct many other higher inductive types from them. So the idea of Lean is really to reduce many of the higher inductive types used in homotopy theory to just quotients and truncation. So there's a result by Schulman and Lumsdaine which says that this cannot be done for all higher inductive types. They have a specific higher inductive type which cannot be reduced. However, there's still many things unclear about higher inductive types. For example, what do we mean by all higher inductive types? There's no general theory of higher inductive types yet, but we will learn more about what there is this afternoon. However, many higher inductive types which we use in practice in homotopy theory can actually be constructed from just quotients. So we can construct something like the homotopy push-out, which gives also the suspension and the circle, which we saw earlier, and many other higher inductive types used in synthetic homotopy theory. We can also construct higher inductive types which not only have point and path constructors, but also two path constructors. So they have they add paths between two paths, and that allows you to construct, for example, the torus and Eilenberg-MacLane spaces. And actually, using just the quotient, you can also construct the propositional truncation And Egbert Rijke has approved that you can also construct N truncations for them. This is not yet formalized, but if we would formalize this in Lean, we could even choose to remove support from truncations in Lean and just have the quotients. Lean has a large library of synthetic homotopy theory, so these are some of the results we've proven. So if you know some of them, this slide is useful for you. If you don't know them, I will not explain most of them. But this is sort of the range what we have. There's a formalization project which has been going on for 1.5 years now to formalize a Serre spectral sequence. And this is almost done. We're very close, which I'm a bit hesitant to say because a couple of years ago I went to my master advisor, Freek Wiedijk, and I also said I'm very close with the formalization, and then it turned out that the paper proof was wrong and I was more than a month off the actual finish. But here I'm confident again that we're close with the formalization, but yeah, we'll see how long it takes. But I think definitely by the end of this program, I strongly suspect that we are finished with this. So I'll tell you a bit more about two of these topics, the long stack sequence of homotopy groups and the Serre spectral sequence. So the long stack sequence of homotopy groups is the following statement. So it starts with a pointed map. So that means that x and y are types with a base point, and f respects the base point. So it sends the base point of x to the base point of y. And then we get the following structure. We get a sequence of groups. These are the homotopy groups of the types. So at the bottom we have the zeroth homotopy groups, and the fundamental groups, and then the higher homotopy groups. And we get maps between them, which makes this an exact sequence, which means that the image of any map is equal to the kernel of the following map. And so this relates the homotopy groups of the domain of F, the codomain of F, and the fiber of F, which is this type we've seen also before. And then so the maps are the induced action of F on the homotopy groups by one of F, for example. Then this is the induced map of the projection from the fiber to X, and this delta is a sort of a mysterious map we construct in the proof. And so this is a very useful tool to compute homotopy groups. For example, if you know two of those columns, then you can sort of figure out what the last column is often. So this is a very useful tool, and this is actually also the basis for the Serre spectral sequence. So if we have a single pointed map, we get a long stack sequence of homotopy groups like this, between the fiber of F, I have to rename this YS, FS, and YS minus 1. But so this is a homotopy group, so a long stack sequence of homotopy groups between the fiber of F, the domain of F, and the codomain of F. But now if you have a sequence of these maps, like this, then we get, for every map, a long stack sequence of homotopy groups like this. And what's nice about this is that many homotopy groups occur twice. They occur in this sequence and in this sequence. And now we can sort of combine these homotopy groups and construct, for example, these diagonal maps, which go from here. You apply this map, you go to this type by just doing nothing, and then you apply this map. So this is the composite of this map and this map. And these maps have nice properties. And this construction forms the basis of what is called a spectral sequence. So the actual construction is a bit too complicated for to go into now. But this is the basis of a spectral sequence, and we can construct a spectral sequence from this. And about 10,000 lines code later, you get the following result, which is the Serre spectral sequence. And I will not give a precise statement of the Serre spectral sequence, but I will give an ID. So it starts with a type X, a family over X to type, and an abelian group G. Then in this expression, there are these things which are cohomology groups. So cohomology group is also an algebraic group you can, well, a group you can compute from any space or type. So it's similar to homotopy groups in that aspect, except that they are harder to define but easier to compute generally. So I'll not give a precise definition, but so these are the cohomology groups. So this is the cohomology group of this total space of F with coefficients in this group G. And this is the cohomology group of X with coefficients in this this group, which is a cohomology group of F of the fiber of F in G. And the statement, the Serre spectral sequence says that in some way this cohomology group of the total space of F is built up from the cohomology from these cohomology groups of the base space. And so indeed this looks like this, which is almost the same formulation, except that there's some reindexing going on. And as I said, the proof is expected really almost done. So I cannot tell you exactly the formulation of the Serre spectral sequence, but I can tell you some of its applications, and that is for the computation of homotopy groups of spheres. So this is a table of the homotopy groups of spheres, which are classically computed. And this is a very central tool, a very central topic in homotopy theory. Often tools are judged, are advertised by how well they can compute homotopy groups of spheres. So these are all the homotopy groups of spheres which are classically known. Not all of them are known in homotopy type theory. Namely, these are known in homotopy type theory, all the colored ones. So everything colored red means it's formalized in homotopy type theory, and colored in blue means there's a paper proof, but it's not yet formalized. So all this blue diagonal is proven by Guillaume Brunerie. That this is Z modulo 2. And all the red groups are formalized somewhere. They're all in particular formalized in Lean. Using the Serre spectral sequence, at least classically, we can compute more homotopy groups of spheres, namely all of these. So we classically, using the Serre spectral sequence, you can compute all the blue homotopy groups shown here. So we can compute like the next 3 diagonals of this table. I'm not claiming here that formalization is almost done, or that in a couple of weeks we will have formalized all these homotopy groups. But this at least shows the power of the Serre spectral sequence, that you can use it to compute all these, as a central tool it's used to compute all these homotopy groups. It also uses other techniques in homotopy theory, like Hurwick's theorem and the universal coefficient theorem, which are not yet proven in homotopy type theory. So there's still a lot of work to be done to compute all these homotopy groups. So because this is there in the audience, there are a lot of people working on automation. I want to say a little bit about automation in homotopy type theory. And basically, in none of the proof systems we use a lot of automation. So in the Lean library, we use a little bit of automation for using type classes. So we use type class inference to infer that automatically infer that some types are truncated, that they are sets, for example. But that is just a simple search, looking at how the type looks and then applying the corresponding theorem. For example, if you have a product of 2 types and you want to show that it's a set, then most of the times this is true because both of the types you take the product of are both sets. and then you apply the theorem which says that the product of two sets is a set. So it would be interesting to explore more automation in Homotopy type theory. So there are a couple complications of this. One is that Homotopy type theory is proof relevant. In general, it matters when you prove a theorem which proof you give, because maybe in the proof you define a function, and that function you want to evaluate, and in general, like all proofs contain some data. And also, when using dependent types, for example, if you have a type dependent over the natural numbers, it matters quite a lot how your theorems and definitions compute. For example, it matters quite a lot if addition is defined on the left or the right argument, and even things like if associativity of addition, how that is exactly defined by induction, that can matter for these dependent types. So those are some complications for doing automation. But there's definitely uses of automation in Homotopy type theory. First of all, there's a chunk of Homotopy type theory where you actually don't care about the proofs. For example, in the spectral sequence, there's a lot of algebra you need to do, which is just set level, group theory, and things like that. And there you really don't care about if you prove an equality, which equality you've constructed. And there, a lot of the existing automation tools could be used to construct equalities in groups, for example, using like an SMT solver or something like that. So one option is to focus on these cases. Another option is to do things like a specialized automation for specific recurring problems in Homotopy type theory. So this is just a beginning of possible discussion for doing automation in HOT. I will leave the rest maybe for discussion after my talk. So some conclusions. So Homotopy type theory is a very convenient language for doing Homotopy theory. So it's more general than traditional Homotopy theory because you can interpret it in any model of Homotopy type theory, including conventional models which show that if you prove something in Homotopy type theory, it will also actually be true for just topological spaces. So Homotopy theoretic notions are more primitive than the traditional definitions, where with primitive I mean close to the foundations, which makes them very convenient to reason with. It gives novel ways of reasoning, like path induction is very useful, a useful tool. It is constructive, but I want to point out it's not anti-classical. So you can consistently assume the law of excluded middle or the axiom of choice if you want, and still do in Homotopy type theory. And that is perfectly fine. And it's possible to verify formally Homotopy theory in practice. So I think that many of the theorems I showed in Homotopy which are formalized in Lean are very hard to formalize just traditionally using set theory as foundation. And the second conclusion is that Lean is a good proof assistant for doing Homotopy type theory, and the reason for that is one sign for that is that we've formalized a significant portion of Homotopy theory in Lean. So thank you very much.
How does the synthetic part of the homotopy type theory interact with the non-synthetic part of where homotopy theory meets mathematics? Like for instance, how would you compute, let's say, the fundamental group of C minus a point? So
okay, so the question is, how does synthetic homotopy theory correspond with the non-synthetic part? So in homotopy type theory I presented today as they are. I think they are sort of two distinct topics. In particular, you cannot do something like take a point out of a space, because all the constructions you do have to be homotopy invariant. So taking a point out of a space is not homotopy invariant, because you might have two types which are equivalent, but if you take a point out of one of them, it's not equivalent to taking a point out of the other one. There are applications of other variants of homotopy type theory, which are like cohesive homotopy type theory, which sort of relates the homotopy theory to the more topological definitions you can set up in homotopy type theory.
But the development, for example, in Unimath that we were hearing about is completely compatible with the synthetic homotopy theory, like in the sense of Martin's slide with the two different kinds. Those are completely compatible developments. One of them is simply happening at the lowest level of the hierarchy of H levels, and it's only working in that lowest level. So
Yeah,
that's completely compatible.
Oh yeah, I didn't mean to imply that they are incompatible,
Yeah.
but to me they feel like two different subjects, which you can do in parallel, but which don't interact too much. Well, I guess you have to do a lot of set theory reasoning to do synthetic homotopy theory.
I have a question about your about the quotient in homotopy type theory. And from the slide it looked to me, but now I want to confirm, that all you get is like sort of three categories, or like you take the R stuff you build in as generators, and then you take like three paths. So
Yes.
would it make sense, or does there also exist a quotient where you can sort of input some notion of equivalence, like in the form of, I suppose, a higher groupoid, and then say, okay, I want this thing to now become the identity type?
Yes. So there, Egbert has done research in that, which is about infinity equivalence relation. So you take some infinity equivalence relation, and then you quotient that infinity equivalence relation to get a type, and then the identity type of that new quotient is exactly the relation you started with. And more specific examples, for example, if you start with a groupoid, you can indeed construct a type, which is the groupoid quotient, which then the fundamental groupoid of that type is then exactly the groupoid you started with. And for example, that last construction you can actually construct just using quotients.
So would that not also be an answer to the previous question? I mean, then I guess when you have, for example, the synthetic spectral sequence, you could just instantiate, like for your type X or whatever, one of these non-synthetic quotients, and like topological sphere or whatever, then apply the synthetic results the same way people would do it in ordinary math.
Spaces are not point sums.
They're not point.
I'm not sure.
Oh well.
Spaces are not groups.
Just to support what you're saying about this is more general than traditional homotopy theory. There's now there are now papers coming out, for instance, about the Blaker's magic theorem, where there are actually new results in higher topos theory by experts in higher topos theory, but building on the work in homotopy type theory. So this is work by people like Andres Real and Eric Vincent, that are actually applying the methods that come out of homotopy type theory in this new setting. So it's actually a generalization of what's happening classically.
Yeah. So for people in the back who maybe didn't hear this, so constructions in homotopy type theory are used in to do similar constructions in higher category theory. Yeah, thanks for your comment.
I have a question about the last bullet point. So this is part of the big proof program. I guess some of your proofs are pretty big, actually. Do you make lean break into a sweat, or is it just breezes through it very quickly?
The type checking in Lean is actually, and the elaboration process they are very optimized, and it's very quick. So I think the whole hot library and spectral library, which in total are like 45,000 lines of code, that takes like 2 or 3 minutes to compile. So it's quite quick. During the proofs, there are definitely cases where it's hard because of the complication that Lean doesn't tell you in the most convenient way what you want to prove, and Lean could have more support for that. That would be useful.
I'm sure Bjarne Strustrup will be very pleased. Any other questions? Okay, let's thank Floris again.